Hello, Jason Hell on behalf of Saber Astronautics. I'd like to welcome you to a talk on a product we're working on called the Predictive Interactive Ground Station Interface. It's a project which we believe is going to be the next generation of space operation software. It's designed right now to sit on your satellite ground station, but the more we look at it, the more we realize it's applicable to being onboard space, the spacecraft itself. So if you think in terms of spacecraft, we've got large amounts of data, large amounts of information. You've got to be able to manage the information to make decisions in any sort of autonomous fashion, and that can have downstream benefits to making things healthier and lasting longer and saving you money in the long run. So that's really what we're about. We are a small company. We're a startup up from Chippendale, but we have a lot of capability. We're packing a lot of punch as far as our technical capabilities are concerned. We've got guys who worked on Hubble and the ISS. We have 2 PhD graduates from the University of Sydney's robotics lab. We've got decorated officers from Army and Air Force Space Command. So yeah, again, a small group. We've got about, I guess we take about 20 interns a year. So our active internship program, we get about 100 applicants. I think that's more of a sign of us being one of the few space startups in Australia than anything else. But real good group of guys to work with. Okay, here's the problem. We all talk about reducing the barriers to entry to space. What does that mean? It means reducing the cost of the engineering of the satellite or reducing the cost of launch. Right, what a lot of people don't realize is that operations actually account for up to 1/3 of the cost of your total mission. Now you look at this screen, you see why. Anybody know what this is from? That's SpaceX. Right? So this is a brand new space operations center. And what you're looking at is they're doing the operations for the Dragon. They got massive amounts of telemetry that they're bringing in that they have to manage. It's a high-risk project, but all the information is just put in a 2D fashion. There's no real context to it. It's just kind of splashed on a screen. And so what you have is this one-for-one relationship between the amount of data that you have to manage and the number of people that you need to hire to manage it. So there's a lot of overhead and labor and in training. It takes anywhere from 12 to 18 months in a professional space operations center, where you have to hire someone and train them up before you can actually use them in operations. So what we're doing differently is that we're focusing on graphic user interfaces, video game technologies applied to the space operations problem as a way of organizing the data. And we're using intelligent diagnostics. So if something does go wrong on a spacecraft or a vehicle on the moon or Mars or on an asteroid or wherever, it's possible to understand why something went wrong so you can make a very quick corrective action and save yourselves a lot of time and money. So imagine you're a space operator using Piggy. Forget about 2D words on a screen. Now everything's in context, it's graphical. You look at the sun because you want to know about any space weather events that can cause damage to your space systems, and there you go, you've got your solar flare. So you've got accurate representations of space radiation that could come from the sun. And you look around the solar system because you want to see if there's a directional component, if you're in the line of fire for some of the directional components of the flare. And you get to Earth and you could click on scientific information, look at magnetic field models like you see here, or you can click on a spacecraft in your inventory and look closely, you get day-night ray casting straight off the graphics unit of your card. So what you really get is real good situational awareness and environmental information. But what you really want to know is what's happening inside the spacecraft, and there you go. You could open it up. You could look inside the guts. You can highlight different subsystems like your structures or your command and data handling like you see here. The point is you now have control over the information you need to see. You don't need to hire 50 people for a spacecraft. You can just do this with one person. Remember that solar flare. Eventually things go wrong with solar flares. And there you go. Components start turning red. Red, that means there's a defect that needs to be managed. Blue means that there's a problem that was on the spacecraft that was impacted by the solar flare that you need to look at, but is recovered. Right? Now the point is that now the system is prompting you, giving you the information that you need to see in order to keep your spacecraft alive and healthy. So that's the graphics. Now we need to talk a little bit about the intelligent diagnostics and bring it a bit into context with space mining is thinking about the types of companies that want to do space mining right now. You've got deep space with DSI, you've got planetary resources, and the idea is you've got these trillion-dollar pieces of material, these asteroids out there that you want to make money from. There's a lot of material that's got to be moved to do that, which means there's a lot of autonomy that has to happen. You have to be able to diagnose your systems in real time. All right, so how do you do that? Well, what you have to do is you have to take massive amounts of data from your telemetry, and then we're going to abstract it into performance metrics, right? And we're going to find the interaction between those performance metrics. And by finding how those performance metrics interact, you can find cause and effect of any defect that happens and trace back up to the actual root problem and make decisions and make corrections. So at Saber, we have a process of analysis that we do first called systems of systems analysis, where we look at the high-level problem that you have, mission statements and modeling goals, and we logically drill down from your mission statement to the systems that you have. And we look into 3 different areas. Right? We look at all the internal actions that your system can have, such as commanding and communications and how you operate. And we also look at anything external, such as your solar flares and whatnot. And then we also look at your information space. And the whole point of going through this process is to answer the question, what are the right metrics? What are the right performance metrics you need to use in order to track the performance of your system? All right, so some of the engineers in the room will look at this kind of funny. It's like, well, don't you already know your telemetry data? Isn't that what you're going to track? And the answer is actually not quite, because you could put too much information by using all the data. You really need to find out what your performance metrics are first in a logical fashion. And then once you have the data, you feed them back up into the metrics. So a single metric ends up being an equation that's data-driven based on your health and welfare telemetry. So top-down analysis, bottom-up refinement, you end up with this map of performance metrics that you're going to use to tell you performance. Okay, once you have your metrics, you have to find a way to get them to interact. You have to find out whether, for example, your space weather is having some type of a causal effect on your electric power subsystem. And you want to be able to track that in a quantitative fashion, right? So the way you read this, call this a system map. These circles represent metrics. And these arrows represent a causal interaction between these metrics, with Bij as some sort of a regression value. Right? So there are a lot of tools out there, and again, the roboticists will find this very familiar, and apologies to the geologists who really don't want to see the map. There are a lot of different ways that if you have a data set, you can find out what those correlations are. Right? You could use linear regression, you could use neural networks. Actually, linear regression works quite well if you have very low dynamic in your system. A lot of linearities in your system, it works quite well. I suspect for autonomous mining, it does not work very well because there's a lot of dynamic. So we looked at Bayesian networks because Bayesian networks have a lot of structures that are very similar to this type of a structure we were looking for. So Bayesian networks 101, just the basics, guys. In a perfect world, if you know what these interactions are a priori, you can, your task is really just to find out these regression values at theta. So the joint distribution is calculatable based on the product of all the local conditional distributions. So you know the product of your metric M3, for example, given you know what M1 is, and you multiply those together, and you've got the joint distribution. And from there, the parameters are just the highest point of a maximum likelihood curve of your observations at Z, given the parameter space. So we have a dynamic system, so we use dynamic Bayesian networks, and we're making a first order Markovian assumption here, where you're no longer based on this prior. You've got your current time step multiplied by that prior distribution. So we've now confused the joint distribution a little bit, complicated it a little bit, not confused it, but still. That's okay, because what this gives us is the ability to look forward in time. If you know what your values are at a current time step and you know it's prior, you could actually estimate that model forward in time. Now we don't know what that structure is in the real world. We don't know what those causal interactions are. So we have to find a scoring function. We have to do a search over all the possible connections and use a scoring function. So we start with an empty space and we iteratively add metrics into the structure, and then we score that structure based on its fit from the maximum likelihood estimate until we have what we find is the closest possible structure. And then you have the scenario that you had in the last slide where you could just find your maximum likelihood. Okay, so it's not just a dynamic system, it's also a switching state-space system. And the easiest way to describe what a switching state-space system is, if you think about it, you can model a human being, and you can model that person walking down the road. And you put sensors on the knees, you put sensors on the feet, and you want to understand performance. And you can model that very accurately with a dynamic Bayesian network. All right? And you can say this is a model for one person walking. The moment that person starts hopping, your model is going to be invalid. So you need multiple models. You need multiple states. All right? For spacecraft, you see the same sorts of patterns in behavior. If you're going to track the performance of a rover on the ground taking a soil sample, for example, you could have one set of regressions. Then you have a space weather event, and your entire model is now changed. You need to have a new set of performance metrics. So the way we model that is with a Gaussian mixture model. And what that does is it discretizes your data set into its different states for you. So each one of those states has its own dynamic Bayesian network embedded in it. So that means at runtime, you train your system in an offline fashion, right? So you've got a set of dynamic Bayesian networks that you're going to switch in between. And at runtime, your Gaussian mixture model, at every time step, you ask the question, where am I right now? What am I looking like right now? What's the closest model that is relevant to me? And that's the model that you use to say this is the measurement of performance at this certain time step. Okay, so that's all fine and good. We've tried this on a lot of different systems, but we have to show that this works for an actual live satellite. So with thanks to NASA Goddard, they gave us all the data for the NASA ACE weather satellite, and it's quite an interesting satellite. It sits at L1, Lagrange point, and it's got 9 sensors that sole mission is to track space weather. So for us, it's a really good data set because now we have data of the spacecraft and we have sensing of space weather. We can find these correlations together and we can do a lot of comparison. So the first thing that we did was that systems analysis where we looked at the entire spacecraft. We actually, we didn't get the design of the spacecraft. We just looked at the telemetry headers. Right, so there's about 1,200 different telemetry items that deal just with the health and welfare of the satellite. And we also had data from the Space Environment Center out of Boulder, Colorado. When we went through this process, we determined that there were about 120 different telemetry items that we wanted to model. And they piped into 22 different metrics related to health and 3 metrics related to space weather. Okay, I'm not going to go through all of these, but some of the metrics deal with propulsion. We found metrics dealing with payload heating. Had a lot of metrics dealing with payload telemetry and electric power subsystems. And of course, you have your metrics related to space weather here at the bottom. So, a lot of people ask me, but what is a metric and why is it important? Well, you've got a lot of different information that's heterogeneous that you're trying to understand on that spacecraft. You got information on temperature, which is totally unrelated to information about electric power. So you have to be able to compare them if you're looking at performance at the same level. You don't want to compare apples and oranges. So a metric is a variable that's data-driven from telemetry that's benchmarked between 0 and 1. Right? So what you have to do, in this example we have a thermal subsystem. You look at the component on the spacecraft that you want to measure performance from. And each component has engineering specifications. And in this case for thermal, we're looking at a computer subsystem, so ranging from minus 45 degrees to 12 degrees Celsius. What you're looking for is a distance function between 0 and 1. So 1 is optimal performance, optimal temperature, and 0 is, if you get past that, you're in danger of having some serious defects. Right, so for NASA ACE, they gave us the entire data set from their launch in '97 up until present day. Actually, I think it was about to 2012 we had. And we wanted to train models on the 2003 space weather event because it's the largest space weather event in recorded history. And we wanted to show that we could use that model time and time and time again ad nauseum in the future. So we're looking for a model which shows properties of time invariance, right, that you don't need to retrain 8 years later. And we're looking for models that have properties that you could say is a general solution. So even though you trained it on a very heavy space weather event, you want to show that it's still valid for nominal conditions. So it's a valid model when things are calm, and it's a valid model when things are rough. So what you're looking at here is you're looking at, on the left-hand side of these graphs, you're looking at the real-world performance metrics from ACE driven directly from their data. And on the right, you're looking at the output from the model, and as you can see, it's almost exactly correct, which means that the model in 2003 worked perfectly well for the space weather conditions in 2009, which are very, very calm, using a lot of straight lines. But I want you to notice a couple of things. What are these spikes here? These spikes are single event upsets, which in the space community are quite dangerous because usually you don't know why it happened. It's the space community's black swan event, right? So to be able to model this in any fashion is actually quite important. And we're actually able to model, we're not getting all of them, but we are getting quite a few of them. Anywhere from 50 to 80% of the time we're able to model black swan events for space weather. All right, so this is a snapshot of the results from 2011, and that was another very large space weather event. And what we want to show here is that we could accurately model a totally different space weather event than what was originally done in our training data. So on the left-hand side, again, you've got a much more active environment, and on the right-hand side, you've got the results from the model. We're quite close. Didn't pick up a whole lot of the single event upsets here, but we're still occasionally getting them. So we're showing some time invariance there. And of course, the piece de resistance for us is we actually were able to go backwards in the model and show the space weather event that caused some of the problems on the spacecraft in the first place. So this is important, really, because you've got the truth on the left, you've got the model on the right. It's almost exactly accurate, exactly what happened. And it's showing that this is a result from space weather event 8 years after the modeling was initially conducted, right? So that's showing very clear time invariance. So a very good result for us, actually, kind of a champagne corking moment. So what does this mean overall? There were anomalies here that we should talk about. What this graph here on the right is, it's showing the distance between the estimate and the actual. So anything over this 0.01, the lower this value, the better, right? Because it's a distance function. So anything between 0.01 and 0.015 we consider a partial solution. And everything over the 0.015 is a failed solution. And we had 22 out of 25 metrics perform very well. A couple did not. We had one of the space weather metrics fail completely. That was the magnetic complexity, the magnetic field modeling. And I think what happened there was the magnetic field actually has a directional component in addition to modeling the strength. So putting those two together, I think this metric is going to have to be split up into two of them. We also had some problems with the propulsion metric. Consider it, we just needed a bit more engineering in the propulsion metric itself. It was just kind of quickly done. So I think what this shows you is a couple of things. You get this cause and effect graph on your left-hand side where you've got space weather having some causal effect on your electric power subsystems, which has some causal effect that you could track on your operational metrics. And that shows you the accuracy that this graph gives you. So your space operators are going to be able to know when they look at this what went wrong and why and how accurate is your information, right? So I did quite a few other tests on real hardware other than the NASA ACE. We're able to show at the Flashline Mars Arctic Research Station up in Devon Island, we did an experiment where we tracked the actual logistics We track the logistics of a human crew in an analog Mars environment. We track what they ate, and we track how much they worked. Two things which you normally would not correlate in certain ways, and we're actually able to come up with a model which drastically improved the logistics estimate for the food. We worked on rockets, worked with CSIRO on a spacecraft structures project, and of course part of the uni days did CubeSat swarms and individual robots. So that's really it. What's next for us is we're setting up a ground station out in Sydney where we do storm forward services for spacecraft. Diagnostics services are ongoing. We can certainly talk to the commercial community about a bunch of very different interesting projects that got nothing to do with space, so I won't bore you with them. But just wanted to show you what we're doing for the rest of the space community, and I just want you to think about what sort of things we need for mining. So thanks for your time.
Questions for Dr. Hill?
You were discussing the need to train this system with a large amount of data. I was just wondering if you want to implement it for, say, a new craft being launched. It seems like how would you, could you immediately implement it, or would you have to have the craft orbiting for a while and gather data and then train the system for that specific craft?
Yeah. We trained the NASA ACE models off of 2 weeks of data.
Okay.
Which it's not a lot, but it is, right? Because you're looking at 1,200 different data points every 16 seconds.
Yeah.
Right? So it's a fair amount. But we're also looking at, especially with some of the new customers we're getting for the CubeSat market, we're looking at recreating these tests with the thermalvac data from thermalvac. Because if you can prove it in thermalvac, then once it's launched, you can have it running right away.
Yeah.
So.
It's a very nice talk.
Thank you.
Enjoyed it very much because I work a lot on stochastic and deterministic systems for estimation. Looking at your model, I mean, you had a real life model and then you came up with your own model for it, right? Yeah, especially there.
Yep.
And those huge spikes that you have on the left side.
Yep.
What kind of an effect do they actually have on the actual system?
Could kill it.
Yeah. So your model will not explain those things. Or is there a...
Well, if in this case,
Yeah.
in this case it's a single event upset, right? In this case, it's explaining only one of these. Because remember, the closeness of these two graphs is what this is really telling you is that the model is accurate. And what the model actually is, what you get at the end of the day, is this guy right down here, right? That cause and effect chain, right? That everything else is saying how accurate this is. So you're right. What we're seeing in here is in this situation we're very good. In here we're accurate. I think this was about 70% of the time for those single event upsets. In here we're accurate except for the single event upsets. And what I think needs to happen is I think we need metrics relating to cosmic radiation. Because we only had 3 metrics and only 2 of them worked for the space weather. Right? So clearly we wanted to do that just to show the space community that we could do this, because in the space community this is totally novel. Even the approach, a lot of the space operations guys will test the waters a little bit with the stochastic innovation, and they'll run away screaming because there's a lot of depth that you have to do in the experiment. You can't just try a little, see if it works a little bit. You really got to go through the rest of the process.
Maybe what you're saying is that the single event upsets are caused by an effect that's unmodeled.
Yes.
Yeah, so the uncertainties in modeling, is there any way of handling that? Would be my following question.
The uncertainties in modeling. Part of the process, there's a whole lot here I'm not telling you guys for IP reasons, but just to answer your question, there's a lot of smoothing that goes on to reduce the uncertainty, and a lot of the process is in determining what to measure and how to measure first before you apply all the stochastic stuff.
One more question. Oh, there was one up in the corner first. Sorry, Aaron. Did I see a question from the back? Yeah.
In sparse application situations where it hasn't happened before, the preferred statistical approach to evaluating phasing brightness?
Awesome question. The the whole benefit of this approach is that if you pick the whole benefit is you've got multiple states, multiple different models you could use. If you have scenarios which don't match, it's going to pick the nearest viable model to you, right? So, and this is the reason why the space community has a hard time with modeling space weather in this sort of global systems model, because you spend all this time modeling one particular event, and it's not time invariant. It's not a general solution. You can't really use it. You have to remodel. We're showing that we haven't had to do that. I mean, the question you're asking, yeah, for us, we were okay for 8 years. Is there another event that completely breaks it? I think the closest thing we'll come to it is something like this slide you're seeing here, where there's something really that's not part of the metric space because we've only added 2 environmental metrics.
Aaron, why don't you go ahead and ask your question as well?
So with all this sensing that you're doing,
Yeah.
can that be done with existing technology on the satellites, or do you require any extra sensors that would add weight to equipment or that sort of thing?
No weight is needed. If you could do it on a ground station, you could do it on the spacecraft. The advantage of doing offline training is that you save that overhead for the development phase. And we are looking, in fact, at putting this on board the spacecraft. And the question is how much computer bandwidth is it going to take? And currently what we're finding is not much. Because it's just, at the end of the day, it's a regression model and a switching state space system. So,
Thank you again, Dr. Hill.
thank you.